Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 5.2.6. Okay, so in the last couple subsections, we've been looking at this diagram. We have shown a condition when f that makes f well defined here in this diagram. So let's assume we have that condition. Now we want to be able to show that this f actually is an isomorphism. We already know that by being well defined in the sense that it preserves the Z module structure. So what we need to know then is it injective and surjective? Let's start with injectivity. How do we know that it is injective? All right. Well, since this is a group map, an additive group map, this is really nice because the fibers partition the domain, and to be injective, all the fibers need to have size 1. And you know, since this is a group map, that all of the fibers are cosets and they all have the same size. So we just need to show that one of them has only one element in it, and then we will be good, and we'll know it's injective. So which fiber should we choose? What about the fiber over 0, the pre-image of 0? Everything that's sent to 0, just show that it's just one element in the pre-image. So this is so in the domain, one element of the domain, only one element will be sent to the 0 over here. That's what we want. Well, we already know that 0 is sent to 0, like the identity over here is sent to the identity over here, because this is a group map and it preserves the operation of addition. So what we need to show is that 0, the identity over here, which is 0 in this component, 0 in that component, is the only thing in the fiber or the pre-image of 0 over here. And then we for sure will know it's injective because all the fibers have the same size. Okay, so let's try that. Okay, so let's see what has what is sent to 0 over here. So we have 0 over here, that's multiples of 12 up here. So multiples of 12 up here. So h of what here, so we take something here, take its pre-image up here, and we send it over here and say, is it a multiple of 12? That's what we're going to be looking at. And if it is, then we know for sure that it is that our okay, multiple 12. Then we know that it's in the pre-image of 0. So we want to show that the only things that actually do that are the zeros that come from here. So multiples of 3 and multiples of 4. We want those to be the only things that will do that and nothing else. And then we would have injectivity. Okay, so let's take a look at what's happening here. All right, so we're looking at the pre-image here. It's made up of things that do this. We just kind of talked about that. So basically we run it through things that are multiples of 12, right? As we send it through. And currently, in order to make this map well defined, we already had a condition. We already knew that this guy had to be sent to 0 mod 4. And let's just recall, E1 is like 1, 0, right? So think the 0 in the second component, that second component is mod 4. So E1 had to be sent to something that was 0 mod 4. And so, and then E2, remember that's like 0, 1. 0 is at the first component, which is mod 3, has to be sent to something that is 0 mod 3. Okay, so we know that, okay, in order for it to be well defined. So we'll use that for now. All right, so we know that E1 has to be 0. We know that E2 has to be, okay, and E2 has to, so 0 mod 4, right? So maybe it'd be better just to write out a 4 because it's a multiple of 4, okay? Okay, so E1 is just, so h of E1, the image of that is a multiple of 4. H of E2 is a multiple of 3. And we got to figure out which A and B, right, will will give you this. And what we want to show is we want to show that that this A and B have must be the 0, 0. So we want that to be 0, 0 only. And so we want to choose H1 and HE2 in such a way. So choosing a multiple of 4 and 3 showed it was well defined. But do we have to have any other condition here and here to make sure that we're actually A and B being 0? So 0 mod. So 0 in the first mod. So 0 in the first mod would be 0 mod 3. So we want A to be 0 mod 3. And we want B to be 0 mod 4. So that's what we want to force. So our choices of HE1 and HE2 need to be such that they force this to be 0 mod 3 and that to be 0 mod 4, and then we would have injectivity. Okay, so what do we need in order for that forcing to be true? Well, what if H of E1 were a multiple of 3? Then that does not force A to be a multiple of 3 at all, because then this would be a multiple of 12 already. So, and over here similarly, for a similar reason, what if this right here were a multiple of 4? Then there's nothing to force that to be a multiple of 4, right? Because then we'd already have a multiple of 12, and the only condition we're really needing over here in the preimage is just for that to be a multiple of 12. Okay, so it seems like we don't want HEV2 to be a multiple of 4. We don't want this guy to be a multiple of 3. We already have what they're multiples of. We don't want it to be a multiple of the other guy. It's kind of what it's looking like, at least right away. All right. Then, okay. So let's just impose that condition right now and see if that's good enough for us, if that actually makes it happen. Okay, does that actually make it happen if we just ensure that that this is not a multiple of 3? Well, if this is not, and that's not a multiple of 4, so if this is not a multiple of 3, then if we mod everything out by 3 across the board, then this is gone, that's gone, those are zeros. So this product will be equal to 0 mod 3. Since if this multiple has nothing in relation to 3 at all, it doesn't even share any common factors with 3 at all, then it has an inverse mod 3. So we can multiply by the inverse on both sides and actually ensure that this is 0 mod 3. So we actually get a forcing here action, that's 0 mod 3. So it actually worked here. And by a symmetric argument, you get the other thing. So that suffices. All we need is, in fact, not only just multiple, but realize what we needed. We also needed that it didn't share any common factors so that we can actually take an inverse of 4 mod 3. All right, in order to force that guy. So essentially what we need, it looks like E1 is going to something 0 mod 4. That's for well-defined, but we also need to know that it's going to something mod 3. Okay, so it's going to something. So E1 is going to something mod 3 here, where, this is, we don't want whatever it happens, we don't want it to be 0 because we don't want it to be a multiple of 3. We also don't want this to share any common factor with 3. So why don't we pick something here that doesn't have any common factor with 3, maybe just a 1. That would be a nice condition. Just picking a 1 here would work, because that would make sure that wherever E1 is sent doesn't share any common factors with 3. If when we mod out by 3, we get 1. There's no way you could share a common factor in that case. Similarly, over here, we can do something like that to something mod 4. In fact, if we just make that star 1, this condition would guarantee the forcing of A to be 0 and then B to be 0 mod 4, so 0 mod 3, 0 mod 4, which would force injectivity. Okay, so that's enough to force injectivity if we just, let's see here, let's get rid of that. And if we just did this, that forces injectivity. Okay, So essentially, just choosing E1 to be any solution of this ensures, because we have a 0 here, ensures it's well defined. Okay, and because we have a 0 here for this solution, means well defined. Now, putting these 1s in here actually guarantees that it is injective. All right, so now this choice guarantees well defined, and that's well defined and it's injective. What about surjectivity? What about that? So let's take a look at that for a minute. Okay, how are we guaranteed surjectivity? Let's look back at this picture for a minute and think about that. So surjectivity means that we're going to get everything down here as we go up through this route, which means at this stage we need to be hitting all, one more than multiple 12, 2, 3, 4 more, 5 more, 6 more, 7 more, 8 more, 9 more, 10 more, 11 more, and multiples of 12. We need to be hitting all of those in here at some point in order for this to be surjective. Now, the way that we run this with H, and really any representatives can come up here at all. Since this map is surjective, we can really take anything here and pop it up here. So let's think about what's happening. All right, so this right here is sent to, so we have any AB happening up here because we can put anything in here and it'll, any AB will be a representative in here. We can pop it up here and we run it through. And when we run it through over here at this side, we're going to have A H of E1 plus B H of E2. And we want this to be able to hit all multiples. So currently, with our current choices, we have chosen H of E1 to be a solution of 1, 0 in the congruences, or mod 3, mod 4, and H of E2, we'd chosen it to be a solution of 0, 1 in the congruences, 0 mod 3, 1 mod 4. Okay, so a solution of this one, a solution of that one. Does that ensure that we're actually going to hit all of the everything in here? Okay, so we're going to at least have a representative in every chunk that we get when we do this merge. Okay, so, and the answer is yes, because these conditions that we have here, knowing that 3 and 4 don't share any common factors, actually ensure that H of E1 and H of E2 themselves, the way that we've written them out, we get something neat happening with H of E1 and H of E2. Let's actually write this out here. So H of E1, we know that it's 1. Let's see, we know it's going to be 1 mod 3. Okay, so we can kind of think of that 1. So it's going to be like 1 plus. Okay, so like 1 plus 3 times t, say, something like that. And then H of E2 is going to be 1 more than a multiple of 4. So you can say like 1 plus 4 times maybe S here. Okay, so then if you take a look at these, so it's 1 plus some multiple of 3, 1 plus some multiple of 4. Now, if you did something like you multiplied, like let A, like where does it come from? Let's let A be 4, for instance, and let's let B be like -3. Now what happens when we multiply this out and add it up? Notice we're going to get a 4 minus 3, which should give you 1. Then over here we'd have 4 times 3 times t, -3 times 4 times s. We have a multiple of 12. We have 1 plus multiple of 12. Wait a minute. So we have 1 plus 12 times something, which is great. So that means 1 is represented down here. It has a pre-image. Well, if 1 has a pre-image, then everything does, because you can multiply this. So you can multiply this by 2, like AB by 2, like let's do like 8 and 6. That would give you 2 plus a multiple of 12. And someone you can get 3 more than multiple, so forth. So we actually get surjectivity from this fact as well, 0, 1, and 0, 1. And okay, so we actually get surjectivity and injectivity. We get both of them, so we end up really getting a bijection. And the whole point is that we had that condition of 1, 0, and 0, 1. So the zeros gave us well-defined, and the ones, putting that in, actually gave us injectivity. And actually, because it was one more than multiple in each case, we just showed that it actually gives us surjectivity as well. Okay, so we have a theorem right here. Now, see, if n and m don't share any common factors, so their greatest common divisor is 1, then if you look at this this Cartesian product of z mod nz and z mod mz, that's actually going to be isomorphic to this. Using the similar ideas to what we just discussed, it can be put into this context for n and m generally. Notice that we used the condition that the GCD was equal to 1, so it didn't share any common factor when we came up with the condition that we were using for it to be well defined. So we just kind of made that condition. Then we got the zeros out of that, and then we looked at that more close. We looked at that again to get an isomorphism with injectivity, and then we used. And then playing off of those details and the choices that we made, we actually showed that the result that we got out of our decisions, which really all stem back from this idea, gave us surjectivity as well. So we do get an isomorphism. This is called the Chinese remainder theorem. And this is the crux for solving these congruences. We're basically looking at a module map that takes us from here to here. All right. And the rest of the section just kind of plays with this a little bit, gives us a little bit of notation. E1 and E2 bar, those are just the images of E1 and E2 in this merge right here in that quotient, so that we can actually represent things down here below in Z mod 3Z cross Z mod 4Z. We could represent them in terms of E1 bar and E2 bar down here if we like. Then we can get this out, just realizing that f of E1 bar is the same as, well, we take the pre-image of E1, it's E1, and then we send it through H, and then we take a bar. That's the definition of F. And so A times the output of F there, and plus B times the output of F there, using the fact that we have outside multiplication by Z down below as well as above, because it's all Z module morphisms, or Z module maps. Thanks for watching.